let's go ahead and get started. Hello, everybody. Happy Tuesday. Happy election day. Thank you for coming. If you haven't voted, make sure you go vote. I planned ahead and mailed in my ballot, so we're good there. But yeah, so make sure that if you haven't gotten a chance, polls close at 7, so you've got some time. In terms of announcements, Talk with the Tech Person is happening tomorrow night. There will probably be pizza. We're having a speaker come in on Zoom, and we'll talk about what it's like in the industry, what the hiring process was like, his work with AI. So it should be good. That's tomorrow in Galileo 114, and it's from 5 to 7 p.m. So if you're interested, head on over there. Make sure that there is some people that I graded off for lab 7, because there was typically like a file that you were missing. Let's see. You can pull it up. Lab 7. I think it was instruction number 7. So just make sure that you're reading all of the instructions carefully. Double check before you submit, because I graded you down if you missed that. So just make sure, and going forward, because there was something in lab 6 as well that, like that one of those first instructions of like write what is new. So just make sure that you're reading the instructions carefully and doing everything that you're being asked to do. Homework 2 has been assigned. Last time we came up with project groups. Let me walk you through it one more time. Because I also, last time, unfortunately, I forgot to unmute myself. So let's do it again for the record. Okay. So this is homework assignment number 2. This is due November 22nd. That should be the Friday before, it should be the Friday before Thanksgiving. So the idea is you get it done Friday before Thanksgiving, then Thanksgiving break, you don't have to worry about it. If you don't get it done then you will have to worry about it over the break. So start now, start early, then you won't have to worry about it during the break. And so you have 2 jobs in this homework assignment. So number 1 is you're going to create a doubly linked list class. So let me zoom in a little bit. So you're supposed to create a DLL class. Let me see if I can hide that. It's a doubly linked list. So let me pull up. I forget where it was. Was it in this PowerPoint? Yeah, it was. So far we've been working with singly linked lists, right? Nodes that have only one pointer and it points to the next node in the list. With doubly linked, the arrows go both ways. So you can not only go to the next node, you can also go to the previous node. With that, so your job is to, based off the LL class that we've done in class and that I gave you in the lab, feel free to use that and just modify what you need to, and just give it a different name. So that's the first goal. You also should have a DL node because our original node isn't going to cut it, right? Our original node class just has data and next. So it needs an additional thing. It also needs the previous pointer. So yeah, so your DLL class should have 3 fields: the size, the head, and the tail. And then I've got this whole big long list of here's the methods that you should have. Most of these are already mostly done from the LL class. So your job is to just extend it a little bit. So with the addition of the previous pointer, what do you need to fix? I'll give you a hint. Most of the work is going to be in insert and delete to make sure that the that you set the previous pointer accurately. Because previously when we delete something, especially, we don't break any of the links. And so technically, if we still had access to that one, we could find our way back to it. We want to make sure that that doesn't happen. So yeah, so make sure that you especially take care of delete. The other big thing in terms of implementation is something that we haven't done in class yet. I would like you to come up with a robust equals method that, so I think the one that I gave you in the lab is just, it checks if the head is equal. I would like you to check element wise, like, is this element, like, if I give you two lists, check if is the first element equal, are the second element equal, are the third element equal. So an element wise operation to check for equality of two lists. And those are the, like, those are the main ones. So equals, insert, and delete, those are the big ones. But I think changes will need to be made to all the existing methods. So I've randomized the groups and I've put them in on Canvas. And so make sure that you, if you haven't already, send an email and try and meet this week if you can, just to get started and start talking about it. My advice with homeworks and with any assignment that has to deal in this class is start early, fail soon. So if you fail quickly, then you can come to me and get help, as opposed to leaving it till near Thanksgiving and then you're in a panic, I'm in a panic. We don't want that. So start early, meet with your group, figure out what you know and what you don't know, and then bring what you don't know to me and ask questions. Okay, that's problem one. Problem one is coming up with the DLL, the doubly linked list. Problem two is to create a deck. So we've made a queue with a linked list, with a singly linked list, right? So your job is to make a double-ended queue. And so a double-ended queue is this guy over here. So it's basically a queue where you add to the back, remove from the front, but there's two additional operations, which is where you remove from the back and you add to the front. So instead of just two operations, there's an additional two for both the back. So you have two operations at the back, two operations at the front. And so I've said, here's where these files should live. So like problem two should live in a package called deck. DLL and node should live in a package called DLL list. So no, wait, how many L's are there? Two. DL list. So make sure that your files are meeting that specification. So this is a practice for you. So where if I give you, here's the code that I want you to write, and you're going to create the project and make the code based on those specifications. So it's a useful skill for you to be able to do. And then the third thing is, well, it's part of problem two, is to just make a simple driver class. You can hard code the data to just add some odd numbers to the front of the deck and even numbers to the back of the queue, remove some stuff from the back, remove some stuff to the front, just to make sure that all the operations are working. So I don't care that much about the driver. I would just like you to have one and to show that your operations are doing what's intended. And as always, please don't start from scratch. You don't need to. I've given you the code from like LL and Node. Use that, start from there. Yeah. So it's a group assignment. So contact your groups today, get set up, set a meeting time, start working on it. And then because it's in groups, only one person for the group needs to submit something to Canvas. Any questions on homework 2? Okay. All right, so get started on that. Email your group today. Okay, so our plan for today we're starting a very important unit. So we're kind of transitioning into algorithms and algorithm analysis. And in order to do that, we need to study what's known as recursion. Recursion is famously tricky. So I apologize in advance. It's going to be tricky. Like, that's just what we get into when we deal with recursion. So I'm going to try and lay it out for you, make sure that you know the basic steps, and then we'll have a lot of practice. So today, we'll do some simple examples together, and then I'm gonna try something new. LeetCode is a website where you can practice for like coding interviews. You can make an account for free, and so what I've done, why did it do that? I've picked out some problems that we can spend as much time as we have today working on these problems. And so the way that LeetCode is set up is on the left-hand side, it gives you a description of the problem. On the right-hand side is where you code it. You can code in all of these nice languages, but since this class is in Java, I prefer and require that you do this in Java. And so then there's some test cases here. So just like the lab, you can run it and see, did your code pass the test cases? So we'll try that a little bit today, see how it goes. We're also doing these sort of things in Tech Club if you're interested in coming by. So so I've picked out a few problems that I would like you to solve recursively, and then we'll see how far we get. And if we finish one of them, that's great. If we finish all of them, that's great. If we finish none of them, that's also okay. And then next time I'll have a lab for you, most likely. Okay. So let's get into recursion. Okay. So recursion is, it's hard to describe. Describing recursion is a bit of a recursive process. So basically a recursive method, so we've been working with methods in Java, like functions, and a recursive method means that this method directly or indirectly calls itself. So that's if we had something that like, I should have put this up before. So like if we have a method called X and inside the method we make a call to X, then that's a recursive method. No, went away. Come back. Okay. All right, so let's say we are in a method, a method called X, and inside the method we make a call to X. X is now recursive. So because we call X inside X, it's recursive. This is something that I see early on when people are learning Java, is especially like in lab 1, where I was like, find the sum of the numbers in this array. And some of you called like the sum method within that. This is something that people do accidentally to start with. Like, I'm just going to call this method and have it do it. And so I see a lot of people like making it accidentally recursive to begin with. So you may have seen this before if you made that mistake. But now we're going to learn how to properly do it and understand how it works. So a recursive method is something that calls itself. That's the key thing. But there's an even more key thing that we need to focus on, is that when it makes a call to itself, it must call on a slightly different or a slightly simpler instance of a problem. So an example for, let's say I have a folder in my computer. So let's come up where it's, I don't know. So let's say I'm in this directory, and let's say I want to process every file in this directory. So what do I have to do? First, I have to process all like the individual files that are here, right? So I have to look at each one of those files that are just here. But I also have to go into each folder and look at all the files in there. So like, let's go to the workspace because that's where all my code lives. And so in order to process the root directory, my 222 folder, I also need to process each one of these folders. And so this is a recursive process where in order to process the root folder, I also need to process the subfolders. But in that, I'm making it a little bit simpler because if I go to like my in-class folder, then I've got to process all of these, blah, blah, blah. But eventually, as I go down the chain, I'm going to get to a folder that just has all files and no subfolders, right? I don't have an infinite directory. Mac doesn't let me do that. So eventually I'm going to mark shapes as check. I've processed this folder. And so then I have to go to another folder. Well, that doesn't have anything in there. So intro is check, all done. For IO, this has all files, process each of those, check. IO is done. And so this sort of process is going to continue. So for every folder, I'm going to process that subfolder. And that's a recursive process where you examine all the files in the subdirectories, the subdirectories, until you get to just all files, and then you can mark that as done. And so once I get to a state where everything in this folder is checked off, then I'm done. So that's the important thing with recursion. We have to end sometime. So it has to end eventually. And so that's why we need to make sure that we're calling, when we use recursion, we have to call on a different or a simpler instance each time. This is really, really important. Another example of a recursive process is, let's say I'm looking up a word in the dictionary. So if I'm looking up the word boon, and I don't know what the word boon means, then actually, let's go through this process. So let's say define boon. And I see the first definition is, this is the thing that is helpful or beneficial. Maybe I don't know what beneficial means. And so then I have to define that. And so beneficial is favorable or advantageous. So what does advantageous mean? If I look at advantageous, then that's kind of a circular process because it links me back to beneficial. But let's say at this point, I know what advantageous means. And so that means I can bring advantageous back to beneficial. And now I know what beneficial means. And then I can bring that back to boon and say, okay, now I know what the word boon means. That's a recursive process, right? So I'm looking up words in these definitions until I know a word, until I meet a word that I know. Like I know what that means. And then I apply that word to the dictionary entry that I was just looking at, and then that word to the dictionary entry that I was confused about, and so on and so forth until I now understand my original word. Doing research projects is also a lot like this. Like if you're looking at a paper and you're like, I don't know what this paper is talking about. I need to look at to try and understand what this paper is doing. and so you go look at another topic until you kind of understand the gist of that paper, and then you can move on to look at the other papers that you've got to look at. So recursive processes are everywhere. We're going to look at how do we code them. So recursion is kind of the other side of the coin to iteration. So we've done iteration a lot in this class. For example, when we are like going through a list, where we start at 0, and then we go to 1, 2, and so forth, right? So that's an iterative process where we're looking at one thing and then the other. Recursion is a different way of solving problems. And a lot of problems are naturally solved by recursion. So one of the most famous ones is factorial. Has anyone seen a factorial before? Does anyone know what factorial is?
Like, so 5 factorial is like 5 times 4 times.
Yeah. Yeah, cool. Okay. If you don't know what factorial is, congratulations. Today's the day you learn. I know I was really happy when I learned about factorial because I thought the numbers were really exciting. So a factorial is written, so like, let's take 5. We write it with an exclamation point, and that reads 5 factorial. And 5 factorial is 5 times 4 times 3 times 2 times 1. And so the way that we calculate a factorial is we say for n factorial, for n being whatever number we want to calculate the factorial of, this is equal to n multiplied by n minus 1 factorial. So you see how this is a recursive process, right? This bit, that's the recursion. But how is it making it simpler? Are we doing the same thing over and over again? No? So how is it simpler? Yeah. Yeah. So we're not just calling, like, if I want to find 5 factorial, we're not just calling like 5 factorial, 5 factorial, 5 factorial, because then nothing ever gets done and we're sitting here waiting forever to find out what this number is. So subtracting 1 from n is making this a simpler instance because recursion must have what's known as a base case. And so a base case is the simplest possible way we can solve this problem. So for factorial, it's well known that our base case is that either 0 factorial and 1 factorial both equal to 1. Like that's no, do not pass go. That's the end point. So once we reach 1 or 0, then that's it. So we'll return 1. And so that lets us do this process of 5 times 4 factorial. And then that returns 4 times 3 factorial. And that returns 3 times 2 factorial. And that returns 2 times 1 factorial. Oh, I know 1 factorial. That's just 1. And so stop. And then once that's done, we multiply all that together. We have our final result of, was it 120? Yeah. So yeah, so this subtraction is critical because if we didn't have that, if we just had like, if somehow we just had n factorial here, that would be circular logic and we wouldn't get anywhere. And you can tell really quickly if you're writing a recursive solution, if it just hangs there and it doesn't do anything, you've probably got infinite recursion and you have to look at it again. Every year I think we're going to go into this and then I decide not to. So who here is taken or is taking Calc 2? Okay, some of you. So there's a chance that if you get to Calc 2, there's a point where you're looking at summation. So like the sum of n numbers, and then you get something that looks like this. Going from I equals 1 up to n, and you just have to add all those numbers together. And part of the thing in Calc 2 is you want to have this proof by induction to say that this formula here is really equal to a nice and tidy thing, like n times n plus 1 over 2. And so the question is, how do we actually show that these two sides of the equation are equivalent? In calc, the way that you prove that is by a proof by induction. And a proof by induction starts with a base case where you say, what's the simplest possible way we can solve this? We can say, so for this example, it would be n equals to 1. And so you can show that like 1 times 1 plus 1 over 2 is just 2 over 2, which is 1, which makes sense, right? The sum of the number 1 is just 1. So we can show this with the base case, the simplest possible way. Sometimes it's not just 1, sometimes it's 0 or however many things for the easiest possible way to show this. And then what you do is you have an inductive hypothesis where you say, let's say it works for k. So let's say it works up to some number k. And then the inductive step is you got to show that it works for k plus 1. And so you use the inductive hypothesis to make your way to k plus 1. And once you've done that, then you're good. Then you've shown that it can work for any number. That's kind of what recursion is like. So the inductive hypothesis and the inductive step are kind of, we can use this strategy to prove that our methods work as intended. But we have the base case and then we have the recursive step. That's what we care about when we're coding a recursive solution. Okay, so we've got some rules of recursion. So the two, number 1 and 2, these are the most important. Where number 1, you must have a base case. If you write a recursive program, I should be able to walk up and ask you, what is your base case? And you point to something on your code and says that's it. The base case is the simplest possible way to solve the problem. So when you're trying to write up a recursive solution, first ask, like, what's the dummy way of doing this? Like, what's the simplest possible way I can solve this problem? And then you have the recursive case. And so for the recursive case, you have to make sure that you are making progress. So I should be able to walk up to you and ask, how are you making progress? And you point, like for factorial, you point to n minus 1. So I'm subtracting 1 from n each time. Therefore, it's getting closer to the base case. The other things is recursion takes a lot of trust. So you have to think it through really carefully and then just kind of take a step back and see what happens. So assume that the recursive call works. If you've put the thought into it, then you are, by a good chance, you're good to go. And then number 4, we'll talk about it with a specific example. Compound interest means that we should never duplicate work by solving the same instance of a problem in separate recursive calls. That's a lot of words. We'll talk about what that means. Okay, so the first thing we're going to do is we're going to do these 3 different examples, and then we'll go work on other stuff. Okay, so let's pull up VS Code. I'll make a new package called Recursion And I'll make a new file in that package. Nope, Java didn't load yet. Let me delete that one and try it again. Recursion.java. There we go. Okay. I'll give you a second to get that all set up. Is that big enough for you guys in the back row?
No. Perfect.
Is that better? Cool. Okay. So we're going to make a method. So I'm going to call the method sum, then capital N. And the idea is we're going to recursively sum the numbers from 1 to n. And we're going to return the sum. So first, let me ask, how do you do this non-recursively? How do we write this with like a for loop or a while loop? If we're given a number n, and we want to add 1 plus 2 plus 3 plus 4 plus blah, 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 plus n, how do we do that?
Yeah, one more time.
If we were to sum the numbers from 1 to n iteratively, so using a for loop or a while loop, how do we do it?
I is less than n. And then I can. Then you have some, or well, you should declare something above that. And then I plus the order. Or, no, sum plus equals I. And then you return some outside of the order.
Mm-hmm. Yeah. If we're adding the numbers from 1 to n,
Then? Yeah, see, oh, less than equal to n.
I might also start at 1. I mean, it would do one extra step because you would just add 0 to start with. So yeah, so we know kind of like, so we know what we're trying to do. We know how to do it iteratively, but now we want to do it recursively. So we know how to do this. I'm going to delete this code. So we need the base case and we need the recursive call. So when we're finding the sum of numbers from 1 to n, what's the simplest possible answer we could give? The answer that we can give without doing any work at all. 1. Yeah. So if n equals 1, then what's our answer? Yeah. Great. Base case, check. If I come up to you and ask, what's the base case for this question, for this method? That one. Simplest possible answer. Yeah, so right. So I deleted the iterative solution because we're gonna come up with a recursive solution. So I did the iterative solution just to remind you, what are we doing? Okay. So for the recursive call, we're going to need to, first of all, we're going to need to return something. We're also going to need to call some n at some point. And so what do you think is a good recursive formulation of this? Yeah, you have,
Then like n. So plus. If you have to iterate, or you have to like subtract down to make sure n minus one.
that works. Yeah. So you could, I don't think you need to. Um,
One, it is, those like else.
yeah, so I think because of the way that we've structured this, we do not need an else. Because if n is one, we're gonna return and we're done with the method. Otherwise, we're gonna return, this is the else case. Especially because we don't have anything after this. So I think we just need the if, and that's fine. I think you could also do this like all in one line if you really wanted to with the conditional operator. I did not prepare this ahead of time, but let's see. So for the conditional operator, we need the condition, which is n equals 1. If that's true, then we return 1. Otherwise, we return n plus some n of n minus 1. Does that work? I'm going to comment this out. It does work. So yeah, so remember way back when we talked about the conditional operator, which is where we've got some condition. So this is for like really simple if else things where we have a condition that's a Boolean, evaluates to either true or false. Then there's a question mark. And then we say, here's what I'm giving you if this answer is true. And then here's what I'm giving you if the answer is false. So this is another option. So what I'm going to do, I'm going to uncomment all of that. I'm going to comment this guy out just so that you know that there's another way of approaching it. So if this makes more sense to start with, go for it. So we've got our base case, the simplest possible answer. We've got our recursive call. Okay, let's test it. Yeah, I should put it in since out. Okay. So let's run this and see how we do. I think those are right. The 5 looks right. So yeah, so with that, we have our first recursive method. Hooray. Let's do factorial. So yeah, question. Yeah, so long is another primitive type. So long is a type of integer. The difference between int and long is how big the number is allowed to be. And so with a lot of these recursive examples, I'll be using long just because the numbers tend to get big. If it gets to the point where long is too small, you can use like big integer, which is a Java type from Java math. And that like expands the size that the number could be, because each number takes up a certain space in memory. And if that number gets to be too big, it causes an overflow, which like is when it resets all the way back around to the lowest negative number. And so that can cause problems when the number that you're working with is so big and then it's like flipped all the way around. One of the fun examples of this, has anyone played Stardew Valley or heard of it? On a real farm? So Stardew Valley has this like cave system where there's technically like an infinite amount of caves that you can go to. Like you can go one level down, one level down, one level down. And someone like modded it to where they go like they break like they cause the level overflow because they I forget the exact number, but like they went so far down that the integer space and memory got overflowed, and so it reset to like -2.7 something. So yeah, so if you need to, you can use the bigger integer. But long is a primitive integer that lets us be a little bit bigger than just int. Okay, so turn to your neighbor and write factorial together. What's the base case? What's the recursive case?
No. So some of us went magnetically less enough to yeah, we weren't allowed to. Back then, we were social variety context. I really never had to. You're older, and something that we have to get enough that, but actually what happened. So I wrote like that. You know, so we have to like, when I was a kid, they used to do like a lot. Yeah. You don't want to zero. You go to zero, then you're gonna multiply by zero. Then I have 1 to 6. Would you be trained? No. We got a Java certification for completing this class.
Get a what?
Certificate.
I don't know.
I'm getting a certificate for after that. I'm wondering if that's like opposite.
Not to my knowledge.
Maybe once I graduate, I can come back and help work on my program. Let me know. Dude, you know in the John's class? Yeah. He was like, in your group, separated into roles here or something. Yeah.
All right, let's come back. All right, who wants to give me their factorial? Go for it.
If. One. And then this would be the current.
Cool. Anyone else have something slightly different?
Yeah, I just made like more programming. Like, I did return n equals 1, question mark 1, colon, n. Sorry, n parentheses n times factorial n minus 1.
Okay, so you'd use the conditional operator. Yeah, I mean, that works too. Like it's equivalent ways of getting to the same thing. Anyone else have something different? Nope. So here's the thing about recursion. You can write a recursive method in a way that looks different from what someone else writes. And they can be doing the exact same thing. So I know I've said this to you about a lot of different things, but like for recursion, it's especially true. So your recursive method may not look like someone else's recursive method, but they can both be equivalent. You just have to you have to think really hard about what yours is doing, what the other person's is doing. Okay. Let's say that we want to yeah, so my other two examples are to print numbers. So let's say we want to print the numbers like let's say we want to print in descending order. So like if I give it 10, then I would expect to have printed 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's the point. It's the sort of thing where the examples we'll start with are you can look at the problem and think, I know how to do that iteratively. Which makes sense because we've been working iteratively this whole time. Recursion is another tool in our toolbox that helps us to solve problems, especially when we get into more complicated things. So let's make a method. I'll call it print descending. And the idea is if n is greater than or equal to 0, let's just, I don't know, maybe we print done or something. And then otherwise we want to print the number that we're at. So work in your groups and just the people that you're sitting around. So I would like you to not only do print descending, but also print ascending. So like that starts at 1 and prints up to including n. So if I give n of 5, eventually I'm going to have 1, 2, 3, 4, 5. So for print descending, it's like 5, 4, 3, 2, 1. For print ascending, it's 1, 2, 3, 4, 5. And so you can just do like just sys out and print the number, whatever that is. So work in your groups and write up your recursive solutions to these two examples. Go for it.
Oh, what's that type of print? Actually.
Yeah. So I would like you to just print something using system.out. and not returning anything.
Oh.
But it can be you can have this formulated slightly different ways where you like return a string or something. But I'm just focused on just print something.
Yeah, you can. You see it? Well, I got my kids to know. They want to see you.
Yeah.
Both. Oh, because everything's okay. Oh, yeah. You wouldn't get it.
That's descending. Ascending is 1, 2, 3, 4, 5, 6.
So.
So we'll talk about this. So with recursion, I think my solution has like 2 lines flip.
And minus 1 plus that. But that would not do the same thing. But that's just changing the order.
Yeah, recursion is tricky. Recursion is tricky. That's what I'm thinking.
And so we not really
Or actually, not it.
recurring is tricky. You're not gonna get your first try, like you feel some kind of means. Metaphor working with the oh. Okay. I mean, I only covered 2 separate. You can shoot it. Oh, that's all right. Anyone else here do oxygen there? Because I don't want like, this the last. You do oxygen there?
I don't
run like. Oh, you run like. You
over a lot of people.
You're gonna be chicken, that's all. You're not health vaccine right now. I completely cut out red meat, tomatoes, peanuts, red 40s.
Sunday?
40s. Yeah. It's real. It's called whoever trapped that in our blood is killed. Yeah, it's not fluoride, it's 44 alpha substances. Watching the movie Dark Water. I've seen it, but I did a project. I'm doing research on it. We're testing water sources for PFAS. No, I need to use their like a $500,000 LCMS laser chromatic mass spectrometer to test for these substances in the water.
So I think
Just
based
testing
on
the water
I
levels.
feel like that's because we can use them.
Yeah.
What's your biggest skill there? But I want to stop it.
Yeah, it was like, you don't do this, you're like, why did I do this? It's not like the fun.
Yeah, you're like, what's the last one?
It's not fluoride, it's polyfluoroalkyl substances. One PFAS. That's not fluoride, bro. I looked up on it's a chemical. Yes,
You have a solution?
yeah, no, I don't want Teflon. It's not very important, yeah. Basically, what's happening is they made this thing called Teflon, and they put it on stuff to make it waterproof, like on a tank. And then Gore-Tex got it too. Gore-Tex got it to waterproof. But what happens is they didn't realize that it doesn't break down. It's a forever chemical. So once it gets into our bodies and our bloodstream, it stays there, and then it leads to like liver disease, like cancer.
Yes.
And
I'd
then
be able to see how this relates to recursion.
well, you can't solve the marketing, and don't wear Arcteryx, don't wear Gore-Tex. The Gore-Tex is actually just a forever chemical. It's very like.
How does this relate to
Because
recursion?
when it rains, it washes off the chemicals into the water stream, and now it's present in 99% of fresh water sources on Earth.
I don't see how that's recursive.
When you think about it, the water cycle is actually recursive. No? Checkmate. said descending.
I mean, it's a cycle. Recursion is kind of, it's a means to an end. Recursion is a
Yeah,
spiral.
what do you think the end is in this? That's what they don't want you to know. The end is the end. It's not even like
Exactly, it's not recursion. Let's focus on recursion.
yeah, I have a problem with how recursive thing.
Okay, okay, so this is confusing, right? Now you're starting to see why recursion is tricky. Let's start with descending. So what should my base case be? If n
Unless you want it to go forever.
or maybe less than equals 0, that's okay. Maybe we want to print done. So maybe like after this, we'll print done. Yeah, so this is the thing that you got to be careful about is if you only have one line of code in your if statement, you do not need curly brackets.
You don't need it, or
If you only have one line of code to execute in your if statement. If you have more than one line, then you need curly brackets. So yeah, so if you do not need, like for my base case, I only want to print done. Or for factorial, if it's at 1 or maybe 0, then I just return 1. No curly brackets needed. If it's anything more than that, if I have more things to execute within my if statement, I do need curly brackets. Okay, so that's the base case. What's the recursive case?
yeah, the recursive case. Wait, what? Then you print n, and then you complement it with n minus 1.
Nope, wrong one.
That's gonna be an else statement for us.
Right, so yeah, so either we put this in else, or yeah, so either maybe we could like, if we chose to add curly brackets here, we can say return. But this is a case where we probably need else. Oops, let me get my brackets all sorted out here. So then, okay, so my recursive case is I print n, and then I call the method recursively for n minus 1. Am I making progress towards the base case? Yes. And what is that progress? Yeah, n's getting smaller each time, and my base case is 0, or less than 0 in case the user gives me some nefarious negative number. Okay, let's test it. Okay, I'm going to comment this line out. And I'm going to call print descending. Let's give it 5. And let's run it. 5, 4, 3, 2, 1, done. It just prints done. Hooray? Hooray. Okay, so that's great. Now, for what should we do for print ascending? Did anyone have any good ideas?
Yeah.
What are your ideas? Anybody else? Okay, so we've got a problem. We want to solve it recursively. Let's see. What do I have in my... Okay, in my notes, I've got several different options. Here's what I think might work. Let's see if I'm right or not. So I'm going to copy what I have here. I'm going to take out these comments. I'm going to change print descending to print ascending. And then I'm going to try and flip these two lines. So whereas before it was print the thing, then make the recursive call, I'm going to try make the recursive call and then print it. Okay, let's see if this works. So I'm going to comment out print ascending just so that we don't get that confused. And let's see how we did. We do print ascending 5. Done, 1, 2, 3, 4, 5. So maybe, I don't know, maybe we don't want to print done beforehand. Maybe we just want to print nothing. I don't know. That's a choice we can make. But this is something that's crucial to note about recursion is that the order that you do things can really, really matter. Why did that work? Excellent question. So, let's draw this out. I'm going to copy this. I would like to make a backdrop. Is that readable at all? Not especially. Let's make all the text black. Okay, there we go. Okay, so this is our method, right? So we've got if n is 0, then either print done or print nothing. That's fine. Otherwise, we call print ascending and then we print something. So let's walk it through. Let's draw this out. So let's say I'm calling, let's shorten it to PA, and I'm giving it 5. Is 5 less than or equal to 0? No. So we go to the else. So we make the recursive call. So we call print ascending of 5 minus 1, which is 4. So now we're in, so this is where like the whole, remember we talked about like the call stack with stacks? This is where the call stack can be really useful for understanding this. So we called main, and main called print ascending of 5. And then we call print ascending of 4. And so now we're in print ascending of 4. Is 4 less than or equal to 0? No. So we go to the else. We make the recursive call, print ascending of 4 minus 1, which is So we add print ascending of 3 to the call stack. And we're in print ascending of 3. Is 3 less than or equal to 0? We go to the else. We call print ascending of 2. This is the call stack, by the way. So now we're in print ascending of 2. You get the gist by now. We go PA of 1, add that. And then that calls PA of 0. Now something different happens. Is 0 less than or equal to 0? Yeah. So it prints nothing, and there's nothing else for it to do in the function, correct? So it prints nothing, and then is done. The method returns. So we had called PA of 0. When a method returns, we pop it off the call stack. PA of 0 is done. Now we are back in PA of 1. We had ended right here where we made that recursive call. Now we can move to the next step. We can now print this number. So since this number is 1, we print 1. Is there anything else left to do for this function? No, because we've done the recursive call, we've printed, and then there's nothing else after that. So the method is done. We return. It's popped off the call stack. So PA of 1 is done. Now we're back in PA of 2. We have done the recursive call. Now all that's left is to print 2. So we print 2, and then we're done. That gets popped. Now we're back in PA of 3. You get the idea, right? So we print 3, PA of 3 is done. We return. PA of 4 prints, returns. PA of 5 prints, returns. And then, since now PA is done, and for us there's nothing left to do in the main method, then main returns and our program is finished. Hooray. Let's draw this out with factorial too, so that we can see when something gets returned. Yes. Okay. So let's draw this out for factorial. This sort of process is something that I encourage when you're writing recursive solutions, like because it's so mind-boggling, you're like, what am I actually doing here? Writing it out like this and understanding what is the recursive call, what are you doing in each recursive call, that's really important to understand. Okay, so we call main, and main calls factorial of maybe 4. So for factorial of 4 is for 1 or 0. No. So we return 4 times factorial of 3. So I'll just abbreviate to F of 3. So now we're in F of 3. So whenever a recursive call is made, we immediately go into that function. So yeah, so we immediately go into the function. We don't continue with F of 4 until we're done with the recursive calls. So now we're in F of 3. Is 3 1 or 0? No. So we return n, which is 3, times f of 2. F of 2 gets added, and then similarly, f of 2 is 2 times f of 1. And then for f of 1, we've hit the base case, so we just return 1. No thinking about it. So what happens for when we're returning something in a recursive case? Can I get you guys to listen up back there, please? Thank you. So when we are returning something, f of 1 has returned 1. And so this, back in f of 2, we had called 2 times the result of f of 1. And so we returned 1. So now for f of 2, we know that this answer is 2 times 1. And so 2 times 1 is 2. And so we return that to f of 2. And so now f of 3 was trying to find out what's factorial of 3. And so it's 3 times, ask f of 2. F of 2 has finally come back and said, here's the answer. It's 2. And so we do 3 times 2, which is 6. And then we give that to whoever called f of 3. And then we do 4 times 6, which is 24. And then we can say, finally, the answer is 24. So the return, it moves up to whoever called it. Okay. So yeah, so hopefully that helps explain factorial. And hopefully this shows you that even very small differences in a recursive program can have a big difference, because for descending and ascending, even flipping 2 lines can give us the exact opposite of results. So you have to be careful, you have to think it through. Okay, let's see. We want to go over this now? Sure, let's do this. So Fibonacci is the case for, what was the rule? So now we're going to look at rule number 4, compound interest, which says that you shouldn't duplicate work. So an example for that is the Fibonacci sequence. So if you're familiar with this, if you're not familiar with this, rather, it's a sequence of numbers, and you calculate the next number in the sequence by adding 2 of the previous numbers. So we start off with 1 and 1, hint, that's the base case. And then we calculate, the next number is the addition of the 2 previous. So 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8, and so on. So we build the sequence by adding each of the 2 previous numbers, and that's our new number. And so let's do this recursively. So before we get started, let's take a vote as a class. One of the things that trips me up and trips the students up every year is, where do we start counting? So either we've got 2 options. Either the first 2 numbers in the sequence are called the 0th and 1st, or they're called the 1st and the 2nd. So this is just whatever makes the most sense in your brain. And if we decide as a group, that's what we're going to go with. So let's call this A, and let's call this B. Who votes for A? 1, 2, 3, 4, 5, 6. 7. Who votes for B? Okay, I think A wins. This is what we're gonna do. So the 0th Fibonacci number is 1. The first Fibonacci number is 0. The second Fibonacci number is 2. Okay.
The first 0.
So the sequence starts with 2 ones. Starts with 1 1. And so this is 0, this is 1, this is 2. So we're going to write a method that calculates the nth Fibonacci number. And so we've decided that we start counting the Fibonacci numbers at 0. Okay. Let's make this long. I'll call it fib. So we are writing a recursive we're recursively determining the nth Fibonacci number, and we assume that 0th is 1, first is 1, second is 2. Okay, so talk with your neighbor and actually, I think we're running a bit low on time. So let's just write this all together. So what's our base case? Yeah, 1 and 1. If let's say if n is less than or equal to 1, that can protect us against any nefarious negative numbers. So this means if we're asking for the 0th or the first Fibonacci number, then we return one. So the 0th is 1, the first is 1. And so our base case is we're just going to return 1. We started. No, so for Fibonacci, we have like 2 base cases. We assume that the sequence must start with 1 1. Because the rule is that we are adding the 2 previous numbers. The 2 previous numbers. Yeah. Yeah. Okay, so if we're adding the 2 previous numbers, what's our recursive case? Fib of what? N minus 1. N minus 2. Yeah, so like, so if we are, let's say we're trying to calculate the 6th. If we know what it is already, so the 6th number is equal to the 5th number plus the 4th number. So once we figure out what those are, we add them together, we've got a result. So yeah, so that's our recursive implementation of the Fibonacci sequence. Good? Let's try that. We may not get to the LeetCode code today. That's okay. Let's calculate, let's see, what's something that we know. Let's calculate the 7th Fibonacci number, which should be 21. So if we calculate the 7th, we get 21. If we calculate the 15th, I don't know what that is off the top of my head. 987. Calculate the 30th. The number is getting bigger. Let's try the 50th. taken a little while.
It's expensive.
So here's the thing. The Fibonacci method, as it is, works. Like, it is technically correct. But the question, as usual, to ask is it efficient? So first, the question is it correct? Is it doing what we want it to do? The second question is this the best way of doing this? Okay, so that finally finished, and it's this whole big long number. But the question is, why did it take that long? So we can represent recursive calls with something that we call trees, and hopefully near the end of the semester, we'll have some time to work with them and learn more what they are. But let's say we're calling fib of 5. So fib of 5 is going to make 2 recursive calls, right? Because in here we have 2 recursive calls. We have fib of n minus 1, fib of n minus 2. 2 recursive calls. So fib of 5 is going to call fib of 4. And it's also going to call fib of 3, right? N minus 1, n minus 2. Fib of 4 is going to make how many recursive calls? Yeah. And 3 is going to call 2 and 1. Two is going to call 1 and 0. So fib of 1 ends, fib of 2 ends, fib of 1 ends. Over here, we call fib of 2 again, which is 1 and 0, which that's fine. Those are our base cases, so that's okay. But over here, we call fib of 3. When we already did all this work over here to calculate what fib of 3 is, we're duplicating work, right? So in the process of calculating fib of 4, we're going to make sure that we know what fib of 3 is. But over here, we're asking to calculate fib of 3 all over again. So this is not actually the most efficient way of doing this, because we are asking it to do this calculation all over again. So the way to solve this is to, we'll look at this in the lab probably, is to do something called memoization. It's not memorization with an R, it's just memoization, which is where we have some sort of data structure that we write, here's what the nth Fibonacci number is, and then we can check, that structure and ask, have we calculated fib of 3 yet? If so, just pull that and use that here, and don't go through the whole recursive process. If we haven't computed the number, then we can compute it recursively, and that's fine. So memoization is another important technique that you should know when doing recursion. Okay. Let's see what else we want to cover. So that's something to know about recursion, is just because it can be recursive doesn't mean it's the best way. Like, the first thing that you come up with may not be the best way of doing it. We kind of talked about this in the example already, where the recursive call is maintained in a stack, in like the call stack of activation records, where it takes the method and it adds it to the stack. And then once it's done, it gets popped off the stack. So my analogy for this is, let's say I am at home and I'm editing a file. And let's say I in the situation where I have a landline, even though I know people don't have landlines anymore. Let's say my landline rings, and so I go and I pick it up, or maybe I'm in my office because I have an office phone. And I pick it up and someone's talking to me, and then my cell phone rings. And so then I say to the person on the phone, hey, hold on, someone's calling me on my cell phone, put them on hold, pick up my cell phone. Hi, what do you want? We're talking. And then let's say the doorbell rings because I have to go sign for a package. So I tell the person on my cell phone, hey, hold on, I have to go to the doorbell. And then I go in and I answer the door, and then the burglar alarm goes off. And so I tell the person at the door, hold on, I have to turn off the burglar alarm so that the police don't come. And so I go turn off the alarm, sign for my package, and then I go back to my cell phone and we finish talking, hang up, go back to the landline, finish talking, hang up. And only then can I get back to the actual work of editing my file. It's a recursive process, right? So a recursive process is like this spiral that it keeps going and going and going and going until it eventually gets to an end point, right? The recursive process must end. Otherwise, we're just going forever. Other recursion examples, we talked about factorial. We'll look at binary search in a bit. So binary search is this thing of where if let's say I have like a stack of papers and they're all alphabetized. And if I want to look for one student, then let's say I want to look for like student J in A through Z. I go to the middle and then I ask, does J come before, what's the middle letter of the alphabet? M. And so if J comes before N, then I disregard the second half of the alphabet and I'm like, throw that away. Then we look at the left side, pick the middle. And then I ask, is this letter before or after J? Then I'll throw away the half that doesn't matter. And I'll keep doing that process, a recursive process, until we get to the exact record that I'm looking for. There's another example, I think it was in the New York Times, where someone's bike was stolen. And they went to the police and they're like, can you look at this security footage to help me figure out who stole my bike? And the person was like, no, there's hours and hours and hours of footage. But the binary search solution is to pick a point in time and ask, is the bike still there? If the bike is still there, then you need to go earlier. And if the bike is not there, then you need to go later. Wait, no. Other way around. So if the bike is there, you need to go later. If the bike is not there, you need to go earlier. And so pick the halfway point and keep doing that process until you get to the point where, oh yeah, I can see is the bike being stolen. That's a recursive process. Another thing is fractals. Let's see if this is what we want. So fractals, this is a sort of recursive structure where you can zoom in on it and it gets to the same thing. So like we've got the Sierpinski triangle. And so you zoom in on part of it and that's just the Sierpinski triangle. And this is itself the Sierpinski triangle and so on and so forth. The Towers of Hanoi, that's also a really famous recursive problem, or a problem that is solved by recursion. So it's this sort of problem, the sort of things that you would like see in a nursery or something. But the idea is that you want to move all of these disks from one pole to the other, but you can only do that by not placing a larger disk. You cannot place a larger disk on top of a smaller disk. And so let me see, can I get out of this to the there's yeah, so there's a bunch of implementations out there of how you actually solve this problem. But you can do this recursively. So recursion is really useful, especially for super complex problems where you can reduce it ever so slightly and eventually get to this finished solution. If you're interested in cryptography, recursion is also used in a lot of the mathematical applications for like modular arithmetic, greatest common divisor. We might see some of these examples in the lab on Thursday. This is going to be one of the problems, I guarantee you, determining whether a number is prime. All applications that can be done iteratively, but is often more elegant looking if we write it recursively. Okay, so to wrap up our recursive lesson, here are the common things that if you're having problems with recursion and you come to me, here's the questions I'm going to ask. Number one, do you have a base case? What is your base case? Is it the simplest possible way to solve this problem? And then I'll look at your recursive call. Is it progressing towards the base case? Is it making it a little bit easier? Something that should be avoided is having overlapping recursive calls. So that's like Fibonacci, where we don't want to have like fib of 3, that's an overlapping recursive call because we do it again somewhere else in this tree. Yeah, and so this bullet point is kind of, it depends on what you're trying to do. If you can do it super simply with a loop, then probably do a loop. But assume for this class, when I ask you to do something recursively, please do it recursively, because that's the point, to get you to learn it. And then the other thing is, especially in light of Fibonacci, don't assume that the recursive call is going to take linear time. So like that it just does it and then we don't have to worry about it, because Fibonacci shows that's not true, right? So if we give it a small number, it computes relatively quickly. But if we give it a bigger number, it takes a lot more time. So don't assume that it's just fast because it's recursion, or it's just slow because it's recursion. It depends on how we've structured the problem, how we've structured our solution, that impacts the actual analysis time. Okay. I don't know that I want to do that activity now. Okay, we've got 5 minutes left. So let's don't know that that may be enough time. Tell you what, spend the next 4 minutes. So in the active learning, no, it's not enough time. Maybe we'll try this. Maybe we'll try this next time. Just if you want to just submit your recursion.java, and in your recursion.java, maybe add like, I'll have this like exit ticket. If you just add like a multi-line comments of one thing you learned and one thing you're confused about, then write that comment and then just submit the recursion.java file. Okay, I'll edit this. Right. And then once you do that and then submit that, you're good to go. Don't forget to take M&Ms as you leave. Don't forget to vote, and I'll see you on Thursday.